In this video, I will be discussing the three-dimensional structure of proteins, and we'll be looking at sections 4.1 through 4.3. Unlike most organic polymers, proteins adopt a specific three-dimensional conformation, and this structure is critical to its ability to fulfill a biological function. The structure is called the native fold, which has a large number of favorable interactions. There is an entropy cost to folding the protein into one specific native fold. The favorable interactions in proteins are the non-covalent interactions that we've talked about, including the hydrophobic effect, hydrogen bonding, the interaction of hydrogen bonds between the hydrogen on a nitrogen and the oxygen on a carbonyl leads to regular structures such as alpha helices and beta sheets, London dispersion forces, also known as van der Waals forces, which are weak attractions between all atoms, and then electrostatic interactions between permanently charged groups. The four levels of protein structure are shown here. First, you have the primary structure, which is the sequence of amino acids. Then you have the secondary structure, which refers to a local spatial arrangement of the polypeptide backbone. And there are two common types, the alpha helix and the beta sheet. And then you have the tertiary structure, which refers to the overall spatial arrangement of atoms in a protein. And this is stabilized by numerous weak interactions between amino acid side chains. And then finally, for some proteins, you have also quaternary structure, which is formed by the assembly of individual polypeptides into a larger functional cluster. In the primary structure, the structure is dictated by the properties of the peptide bond, also known as the amide bond. The amide bond exists in a hybrid of two resonance structures. As a result, the resonance causes the peptide bonds to be quite rigid and nearly planar and exhibit a large dipole moment. So if we look at an amide, we could draw it like this, or we can draw the other resonance structure where there's a carbon-nitrogen double bond. And this structure contributes quite a bit, so there is significant double bond character between the carbon and the nitrogen, which makes the amide bond quite planar and rigid. Now, while rotation around the peptide bond is not permitted due to that double bond character, however, rotation around bonds connected to the alpha carbon is permitted. And there are two terms we refer to when discussing the angle around the alpha carbon amide nitrogen bond and the alpha carbon carbonyl carbon bond. This one is called the phi angle, and this one is called the psi angle. In a fully extended polypeptide, both the phi and the psi are 180 degrees. Now, the organization around the peptide paired with the identity of the R groups will determine the secondary structure of the protein. We can think of the polypeptide as made up of a series of planes linked at the alpha carbons. And in this, the carbon-nitrogen bond can't freely rotate, but the nitrogen-carbon alpha and the carbon-alpha-carbon bonds can freely rotate. The rotation about the nitrogen-carbon alpha bond is described by the phi angle, and the rotation around the carbon alpha carbon bond, this bond, is described by the psi angle. Just as a refresher, a dihedral angle is the angle between two intersecting planes, and in chemistry it is the angle between planes through two sets of three atoms. So for example, we have this plane here and this plane here, and the angle between those planes is the dihedral angle. It turns out that some phi and psi combinations are very unfavorable because of steric crowding of backbone atoms with other atoms in the backbone or side chains, whereas some are very favorable. And that's due to the chance to form hydrogen bonding interactions along the backbone. And there's a plot called the Ramachandran plot, which shows the distribution of favorable phi and psi dihedral angles commonly found in proteins. So this is a Ramachandran chart. and the values for phi and psi for various allowed secondary structures are overlaid on the plot. Secondary structure refers to a local spatial arrangement of the backbone, and there are two main types, the alpha helix and the beta sheet. There are also irregular arrangements of the polypeptide chain, which we call the random coil. For these different secondary structures, there are idealized phi and psi angles shown in this table. So for the alpha helix, the idealized phi angle is minus 57 and psi is minus 47. In the alpha helix, the backbone is held together by hydrogen bonds between the backbone amides of an N and N+4 amino acid. So here we've got the nitrogen atom with its hydrogen, and it's forming a hydrogen bond with the carbonyl oxygen of a residue at N+4. It's a right-handed helix with 3.6 residues per turn, and each turn has a length of about 5.4 angstroms. And the peptide bonds are aligned roughly parallel with the helical axis. The side chains point out, roughly perpendicular to the axis. Here is a picture of a right-handed versus a left-handed helix. So if you have your thumb pointed up following the rise of the helix, then look at how the fingers are curled. And if they curl like your fingers in your right hand, then it's a right-handed helix. And if they curl like your fingers in the left hand, it's a left-handed helix. Another way to do this is to start at the bottom and follow the helix up. And if it goes in a clockwise direction, it's a right-handed helix. And if it goes in a counterclockwise direction, see this, how I'm going counterclockwise, it's a left-handed helix. Here are some different depictions of the helix. A here shows a ball and stick model showing the interchain hydrogen bonds, and the repeat unit is a single turn of the helix, 3.6 residues. This B is a view of the alpha helix from one end looking down the longitudinal axis. And note the positions of the R groups. They are purple spheres that are pointing out from the helix. Now I will tell you that the ball and stick model used here gives the false impression that the helix is hollow because the balls do not represent the van der Waals radii of the individual atoms. So it's not correct to think of it as a hollow helix. C shows the space filling model, and this indicates that the atoms in the center of the alpha helix are in very close contact. And then this is another representation called the helical wheel projection. And this representation can be colored to identify surfaces with particular properties. For example, the yellow residues could be hydrophobic and conform to an interface between the helix shown here and another part of the same or another polypeptide. The red and blue residues illustrate the potential for interaction of negatively and positively charged side chains. Here is a video of a protein, and we're going to strip away everything down to the backbone. And then you could see how it does look like an alpha helix when you're just looking at the backbone. Here is another representation of that alpha helix. And then this movie shows the side chains, how they're on the outside of the alpha helix if you're looking down the alpha helix. This video is going to show you the hydrogen bonding that is responsible for keeping that alpha helix in place. So here we have a hydrogen on nitrogen, hydrogen bonding with a carbonyl oxygen. And look at how those hydrogen bonds are dispersed throughout the alpha helix. This movie shows the different residues for each turn. So there's approximately 3.6 residues per turn in the alpha helix. Not all polypeptide sequences adopt alpha helical structures. Small hydrophobic residues such as alanine and leucine are strong helix formers. However, proline is a helix breaker because the rotation around that nitrogen carbon alpha bond is impossible because it's in part of a ring. Also, glycine is a helix breaker because the tiny R group supports other conformations. In addition, attractive or repulsive interactions between side chains 3 to 4 amino acids apart will affect formation. This table shows the propensity of amino acid residues to take up an alpha helical conformation. So the larger this number, the greater the free energy change, and that reflects a greater difficulty adopting the alpha helical structure. So you can see for alanine, it's 0, but for glycine, it's quite large. So the amino acids with large numbers here do not want to adopt the alpha helical conformation. The next type of secondary structure is the beta sheet. And in this, a sheet-like arrangement of the backbone is held together by hydrogen bonds between the backbone amides in different strands. Side chains protrude from the street, alternating in an up-down direction. Multi-beta strand interactions are called sheets, and there are two orientations, parallel and anti-parallel. Parallel sheets have strands that are oriented in the same direction, and anti-parallel streets have strands that are oriented in opposite directions. So notice here, this is a parallel beta sheet. The hydrogen bonded strands run in the same direction. Now the hydrogen bonds here are bent, which is a weaker hydrogen bond. So notice here we have the N-terminus on the left and the carboxyl terminus on the right. In contrast, here is the anti-parallel beta sheet. So we have the N-terminus here, but then we have the carboxyl terminus here. So they are going in different directions. And then here we have hydrogen bonds between the strands. So here's a hydrogen bond between this hydrogen on the nitrogen and the carbonyl oxygen. And notice the linear geometry for that hydrogen bond, which equals a stronger hydrogen bond. This is a picture of a beta sheet. So if we zoom in on one of the strands, we can see that the backbone actually looks kinked, which is why we give it that pleated depiction. This movie illustrates the hydrogen bonding between different beta strands in a sheet. The next topic is beta turns. They occur frequently whenever strands in beta sheets change direction. The 180-degree turn is accomplished over 4 amino acid residues, and it's stabilized by a hydrogen bond from a carbonyl oxygen to an amide proton 3 residues down the sequence. Proline in position 2 or glycine in position 3 are common in beta turns. These are two types of beta turns. Notice the only difference between these two is whether this carbonyl is pointed out towards you or away from you. So as a polypeptide changes direction at many points, whenever direction is changed, there's a turn. And this is shown in the movie here. So the arrows are one representation of beta strands, and then the segments in blue would be the turns. This shows the beta turns, and if we zoom in on one of those beta turns, you'll see that it's composed of 4 amino acid residues. And then if we look at those 4 amino acid residues, we can see that there is a hydrogen bond between the first and the 4th amino acid residue. So here we have that hydrogen bond I just showed you, and here in this particular one you might have a glycine residue, which is common in beta turns. Most peptide bonds that do not involve proline are in the trans configuration. By trans configuration, we mean that the alpha carbons are on opposite sides. So this would be an alpha carbon here. This would be an alpha carbon, and they're on opposite sides of the CN bond. In contrast, a cis conformation for a peptide would have the alpha carbons on the same side, and it would look like this. See how now they're on the same side of that carbon-nitrogen bond. So most peptide bonds adopt the trans configuration. And the reason for this is you don't want the alpha carbons bumping into each other. That causes a lot of steric strain. Now that being said, peptide bonds involving proline, about 6% of those are in the cis configuration, and most of those involve beta turns. So this would be an example of the trans versus cis peptide with a proline residue. So here you have your alpha carbon here. Here we got an alpha carbon here. So notice that the alpha carbons in the trans are on opposite sides of that carbon-nitrogen bond, but then in the cis configuration, they're on the same side. Circular dichroism, or CD analysis, can be used to determine the types of secondary structure in a protein, and in this it measures the molar absorption difference of left and right circularly polarized light. And here you can see the characteristic wavelength absorptions for various secondary structures. So the alpha helix, the beta conformation, and the random coil all have different absorptions. By using this analysis, you can get a rough estimate for the fraction of the protein made up of the two most commonly occurring secondary structures. Let's move on to tertiary structure. So that refers to the overall spatial arrangement of atoms in a protein. It's stabilized by numerous weak interactions between side chains, largely hydrophobic and polar interactions, and it can also be stabilized by disulfide bonds. There are two major classes, fibrous and globular. Globular proteins are water or lipid soluble. This movie shows the tertiary structure and how it can be stabilized by interactions between residues that are very far away. But when the protein folds, they actually become close in space. This is an example of collagen, which is a fibrous protein. And the chain of collagen has a repeating secondary structure unique to it. It has a repeating tripeptide sequence, shown here, which adopts a left-handed helical structure with 3 residues per turn. 3 of these helices, shown here in white, blue, and purple, wrap around one another with a right-handed twist. There is 4-hydroxyproline in collagen, which forces the proline ring into a favorable pucker and offers more hydrogen bonds between the 3 strands of collagen. The post-translational processing is catalyzed by prolyl hydroxylase, which requires alpha-ketoglutarate, molecular oxygen, and ascorbate, also known as vitamin C. The fact that collagen requires prolyl hydroxylase, which requires vitamin C, indicates that if you don't have enough vitamin C, that will result in a breakdown of collagen. And indeed, scurvy, which results from a lack of vitamin C, does indeed result in collagen not being formed appropriately. This table illustrates some of the structures and their corresponding characteristics. So if you have an alpha helix cross-linked by disulfide bonds, that results in tough and soluble protective structures, which is found, for example, in the alpha keratin of hair. If you have beta conformation, that results in soft, flexible filaments, such as in silk. and then the structure of the collagen triple helix results in high tensile strength without much stretch, and that is found in the collagen of tendons and bone matrix. This is the structure of alpha keratin in hair. It is a 2-chain coiled coil. These coiled coils combine in higher order structures called protofilaments and protofibrils. And then 4 protofibrils, 32 strands of alpha keratin in all, combine to form an intermediate filament. Silk fibrin is the main protein in silk for moths and spiders, and it has an anti-parallel beta street structure with lots of alanine and glycine side chains, and it's stabilized by hydrogen bonding within the sheets and London dispersion interactions. Here is an image here, and it shows the glycine and alanine side chains. This movie shows the different beta sheets and how they are layered on top of each other, and notice that they're anti-parallel. Spider silk is extremely strong. In fact, it's stronger than steel, but it can stretch a lot before breaking. In a globular protein, different segments of the polypeptide chain fold back on each other, generating a more compact shape than is seen in the fibrous proteins. And here are 2 different views of the same protein. This is the myoglobin of the sperm whale. A shows the ribbon representation, which highlights regions of secondary structure. You can see the alpha helical regions, for example. And B shows a surface contour image, which can be useful for visualizing pockets in the protein where other molecules might bind. Motifs or folds refer to specific arrangement of several secondary structure elements. They can be found as recurring structures in numerous proteins, and globular proteins are composed of different motifs folded together. So these are examples of 2 motifs, the beta-alpha-beta loop and the beta barrel. Here, this illustrates how the alpha-beta barrel is constructed from repetitions of the beta-alpha-beta loop motif. There are protein segments that lack definable structure, and these tend to be composed of amino acids whose higher concentration forces less defined structure, such as lysine, arginine, glutamate, and proline. And disordered regions can conform to many different proteins, facilitating interaction with numerous different partner proteins. Finally, the highest level is the quaternary structure, which only certain proteins have, and it's formed by the assembly of individual polypeptides into a larger functional cluster. Here, A and B show 2 different representations of deoxyhemoglobin, which is comprised of 4 polypeptide subunits packed together. And those are further defined as having alpha subunits and beta subunits. The alpha subunits are shown in shades of gray, and the beta subunits are shown in shades of blue. And that is it for this video.